Hi everyone. So welcome to this series of binary search problems. So today we are going to discuss another interesting problem on binary search. So let's just get started with this. So we are actually given a matrix of elements where each row and column of the matrix are having elements in non-decreasing order. So non-decreasing order, as I have stated in the example below, like if we consider this particular row or any row we are having elements in increasing order, which is non-decreasing. Okay, and if we take any column, then we can also see that each column is having elements in increasing order from top to down, right? So the question is that we need to find the target element which is being provided to us. So let's just say that if target provided to us is 10, so we need to find if this 10 element exists in this matrix or not. Okay. So there are multiple ways to do this. Like I'm going to discuss three ways going from brute force to the most optimized solution. Okay. So the very first thing is that while looking at this particular problem and searching for an element, it is very easy problem as you would see. It is just searching for an element in the matrix. So one of the most brute force solution is that we can iterate over the complete matrix and look for the element or look for the target. If it exists in the matrix, we return true. If it doesn't, then we return false. But again, if we are provided with this sorted matrix, like someone is doing these efforts to actually organize and sort this matrix for us, then they won't want us to actually, do this iteration over the complete matrix and then give us a result, right? So we need to utilize the feature of its sorting. So the brute force, one of the solution is that iterate over the complete matrix and check if target exists. So the time complexity is going to be what? We are iterating over the complete matrix. So the time complexity is going to be rows times the number of columns which are there in the matrix. And the space complexity is definitely going to be constant because we are not utilizing any extra space as such. Now the second solution that let's just utilize the property of its sortedness. Okay. So as you would observe from this example, one thing is that the very first element or the 0, comma 0, that is 0th row and 0th column of this matrix is always going to have the smallest element of the matrix since this matrix is sorted, right? And at the very end, which is row minus 1, col minus 1, right? So at the very end, we are going to have the largest element in this matrix. Okay. So one thing is that since this matrix is sorted, we need to find a certain position from where we could start our journey to actually look for the element, right? So let's just say that we start from the very first element. Okay, let's just consider that very first element we start from here, 0 comma 0 position. Now if our target is 10, right? So since this element being the smallest element, okay, if the scenario is that our target is 1, then it's just very fine for us. Like we can just simply return that result. But what if our target is something else? Then the issue here is that if we try to, compare 1 and 10, then 10 is going to be greater than 1. And since 10 is greater than 1, then ultimately, where do we need to go to actually look for 10? That becomes a bit confusing, or that becomes impossible for us to decide. Because we are having both the directions. We can go even diagonally, we can go in the right hand side in the column wise, or we can go row wise, bottom. We are having all the three directions in which if where our target can lie. If we ignore the case of even diagonal, so we can clearly state that even if you go to right or even if you go to bottom, our target can lie in any of these areas. Okay, if we start from zeroth index. Okay, so we cannot even decide from if we are considering this index as the starting position, that we cannot decide in which direction we need to actually look for. our element. Now, same likewise goes to the very last element, that is the greatest element. Since our target element being smaller than the greatest element, definitely, so we can again cannot decide in which direction we need to go to actually look for our target element, because our target element can even lie in this particular row as well, or it can even lie in this particular column as well, which is traversing over this 100. So again, it becomes confusing or ambiguous. It becomes impossible for us to even decide where do we need to go. Then where can we start from? If we start from any random position, you would say, right? Let's just consider any random element. Let's say 25. We consider. Then again, this thing will happen for us, because 10 being smaller than 25. Again, we are having two positions in which we can actually search for that element. Right? We can go to left, which is 14, and we can go to above, which is 6. Right? We cannot decide ultimately. So if we observe carefully, right, for this top right element, right, for this element, the element to the left are smaller than this element, and the element which is lying below it are the ones which are actually greater than this element, right? So if we consider that our target is 10, so we can say that if 10 is greater than 5, we can definitely be 100% sure that it is not going to lie on the left hand side of this element, or even for that sake, it is not even going to lie above this element. That is, column wise, if there exists a row above this, it is not going to lie there. Right. Reason being, because since this matrix is row wise and column wise sorted, so as we go down the column, we are actually increasing the element. Yeah, right. We are increasing. Our elements are increasing, and as we go towards the right, like from here, if we go to right, in that situation as well, our elements are increasing. So here we can actually decide that if the element or if our target is actually greater than this, we can actually be 100% sure that we need to go. We can go towards the bottom. That is, row wise we can go down. Okay. So now we are at 12. So now at 12 position, if we compare, we observe that 10 is actually smaller than 12. So in that situation, now we can again be 100% sure that we don't need to look row wise down. We don't need to go down, because ultimately if we go down, we are actually having greater elements than 12. So we actually need to go left, because by going left, we are going to have elements which are smaller than 12. And there we can have the possibility of having 10 as our element. Okay. So now we move to left. Now 9 comes. Okay. So now 9 is actually what? 10 is actually greater than our 9, right? 10 is actually greater than 9. So now again we have the possibility that if 10 is greater than 9, and we are actually coming from the right hand side itself, which is from the greater element than 9, right? So ultimately we can clearly state that okay, I am coming already from the greater element and I'm not able to find this element here. So we can clearly state that this element actually doesn't exist in our array, because going to the left is actually decreasing the element, right? If we go to the left to search for 10, it is not correct, because ultimately all the elements to the left of 9 are going to be either smaller or equal to 9. Okay. So and if we go to down, then again the elements are going to be greater than 9. But we are already coming from the right hand side itself, so there is no point of actually going towards the bottom or even going to right and go to check for it. Okay. So we can clearly make this observation from here that okay, our element cannot lie here. But again, what we can do is we need to have the terminating condition. So the one thing which we can observe is that if the element or if the target is greater than the element of matrix, we go bottom, row wise down, and if the target is less than the element of matrix, we go column wise left. Okay, so we can again say that since the 10 is greater than 9, so our element is going to lie below here. So from 9 we can move to 28. Then again from 28 we say that 10 is smaller than 28. So we move to left. We move to left again from here. 10 is less than 25. We move to left. 10 is less than 14. We again move to left, and then our terminating condition will be encountered here. So the thing to observe here is that at 9 we didn't stop. We actually continued according to these conditions. That if our target is greater than the matrix element, we go row wise down always. And if our target is actually less than the matrix element, we go column wise left. And ultimately we will, this thing will continue till the time our index are out of range, or if the element is if the target is found. If the index is out of range, then ultimately at then we can return false, and if the element is actually found, we can return true, right? So one of the solution is by utilizing the sortedness of the matrix, we and by observation we came to this particular solution, right? So let's just code this out. What it is doing is that let's just define this function for matrix traversal. Okay. So what we are doing here is that we are actually iterating over this complete matrix. So we need to define a certain index and the edge case or the edge condition where we need to end our matrix. So what we actually require is the rows, that is the number of rows in the matrix, the column, that is the number of columns in the matrix, the start index, that is again where the starting index from where we're going to start from, and the end index, that is the you can say the start index is basically the starting row position, and you can say the starting column position for this, and the matrix itself definitely. Okay, so this matrix is going to be our number array of numbers, right? So now in this solution what we are doing is we have defined our starting column and the rows. So we can consider a while loop because we need to iterate to based on these conditions. We will continue iterating till the time our indexes are out of range or if the element is not found. Okay. So let's just define the return type of this particular function as Boolean. Okay. So now we can say state that if our start row, okay, if our starting row is less than rows, and if our starting column is less than calls, and or you can say just if this condition, if the index is within range, then we can define our three conditions. First is that if target is greater than matrix element. So what do we do if target is greater? We go row wise down. So what that is, like what that means is that we increment our starting row itself. So let's just say that and we also need to have the target. I didn't take the target. Okay, so now if our target is actually greater than my matrix starting row and starting column position, then we can say clearly state that we need to do what? We need to go row wise down because our target is greater than our current element, so our target can only be found in the bottom positions or the row wise down positions. So we increment our starting row by 1. Else if our target is less than the matrix starting row and starting column, then we can clearly state that we need to go column wise left. That means going left is decrementing our column index by 1, right? And else if neither of these conditions are there, then ultimately we have found our target element, we can clearly return true from this here. And if now this is a condition where we have actually found our target. So the breaking conditions were that if the ranges get exhausted, if our element or if our indexes go out of range, or if the target is not found. So we have encountered, like we have dealt with those, the situation where the element is actually found. Now the this while loop will only break if our indexes, the starting indexes, goes out of range. And in that situation, what it means is that were not able to find our element. So we can clearly return false here. Okay, so let's just see what this has to state for us. Like, let's just check if whatever what we have written is actually correct or not, right? So we are having rows, we are having columns here. The starting row, right? So starting row, we are going to start from the very first row of this matrix, right? We are going to start from the very first row of this matrix, and that too from the last column. So the last column we can define as false minus one. Okay, the target element, let's say again it is 10, and the matrix which we have already defined as it is there. Okay, and yeah, I forgot to pass it inside the function. So matrix traversal, I've done this. Okay, so let's just see. Okay, it returned true, and why is that? So if a target is less than the matrix starting row in the starting column, we can say we decrement this. And if our target is greater than the starting row in the starting column, then we increment our row. So why it is actually returning true here? This is my target element, right? Target. Okay. Is there 10 element here? Or no, there is no 10 here. So how come it actually found the element? That's interesting. So let's just do one thing. Let's just state here that for what actually positions it actually found. So that is going to be matrix starting column and starting row. Right. Let's just see that at what position is actually finding. Okay, I'm gonna find matrix starting row and starting column. Oh, starting row and starting column. That's undefined. Okay. So starting row I incremented and column I decremented. Okay. One of the base conditions which I actually missed here is that we already only checked if the indexes are less than rows and the columns. But what if the indexes are going negative? Like if we are going column wise left, right? Our column is actually going to decrement by into negative indices, and in that situation needs to be handled. So we need to have a also check for this thing, right? Like if our starting column is greater than equal to 0, because ultimately we are always incrementing our rows. Okay, so this condition won't be required where we need to check for columns being greater, because the thing is that since we are going column wise left, right, we are starting from the top right position and we are going column wise left. So what will happen here is that our columns are always going to be decremented, so they cannot be greater than the column. Okay, and since our rows are always increasing and while going down, so they cannot we cannot put, like, we don't require to put a check for rows greater than equal to 0, because they are always going to be greater than equal to 0. So we just need to have the check that if the rows are less than the number of rows actually provided, the row index is less than the number of row index which is provided, and the column is actually greater than equal to 0, because by column wise we are going left. Okay, so in this situation now it will give us the correct result, that is false. Okay, let's just consider another example. Let's say 34. If again return false, now let us consider this 70, which is actually the part of our matrix. Okay, so it returned true. Okay, so this solution seems to work fine. One thing to also observe here is that there are two positions actually from where we can start. So one is which I already told, that that's the top right. But can you guess what the other position could be? See, it is clearly the bottom left. Okay, so why is that? Because again, if we observe from the same observation as from top right, like for top right elements to the left of it are smaller, elements lying down are greater. For bottom right, the situation reverses. So element to the top of this bottom right, bottom left element are actually smaller than this. Element to the top are smaller and element to the right are greater. So we just need to reverse these conditions in order to handle that situation. So we are having both the positions to start from. We can either start from top right, which I currently discussed, and we can start from bottom left as well. For bottom left, I would like that you actually write the code for it. It will be just small code changes here. The overall algorithm is going to remain the same. Okay. Just for practice, you can write the code for the bottom left as well. Now, the important thing is the time complexity which we are dealing with here. So, what would be the time complexity? Are we traversing over the complete array? Right, we are not actually. We are not traversing over all the elements of the array, right? Since we're utilizing the sortedness of the matrix, we are not actually traversing over the complete array. We are just moving row wise downward or column wise left in order to actually find our element, right? So our time complexity is definitely not going to be in the n square, you can say. It is not going to be rows times columns. Our time complexity is going to be rows plus the number of columns, right? And why is that? Because the worst case scenario is that, let's just consider that if we are starting from the top right position, okay, if we are starting from this top right position, that is from 5, and if our element to search for is 33, okay, so what we will end up traversing over all these rows, right? We will end up traversing through this complete column, and in this row we will be end up traversing over all the elements of this row towards the left. So we can say that this complete column and this complete row will be traversed, and this, in that situation, since this is a form of a linear traversal itself, so we can say that the total columns, that is number of columns plus the number of rows, is going to be the overall time complexity here. And the space complexity is going to be 1 because we are not using any extra space, right? We are just using the variables to actually decide for us that where do we need to go. So this is one solution in which we are, this is a more of, you can say, linear solution. So you can say that if there are n number of rows and n number of columns, so we can say that the time complexity of the above brute force solution where we are doing linear traversal was n square. And here, since we are traversing over the row or column only once, we can say that the time complexity is going to be linear, that is O of n. Now, question here is, can we further improve this? Okay, let's just say that our matrix size is quite huge. Okay, if it is ranging in the in 10 raised to the power 8, the sizes. In that situation, again, this solution will falter because the linear approach will be that we are traversing over 10 raised to the power 8 or 10 raised to the power 9 matrix. So this solution will tend to falter in that situation. So how further we can optimize this? So since this series is, as you guessed, of binary search, so binary search actually again comes to rescue here. Okay. So now let us observe like how binary search is also actually helping us here. So here, if you would see that this matrix is sorted. Okay. Now let's just consider a different example. Let's say we are trying to find for 27. Okay. Now, if you would see for binary search, let's just consider this very first column. Okay, binary search can only be applied to a linear matrix. Okay, we have always applied binary search to a linear array, right? So let's just consider the same thing. Let us just pick one particular array. I am picking column wise array. Okay, this very first column I am picking 1, 5, 14, 31, and 33. I am picking this very first column. Okay, let me just highlight this for you as well so that it becomes more clearer. I am picking these elements for my binary search first. Elements of this column. Just give me a second. Okay, so now I am first considering this particular array. Okay, let us just forget about everything else here. Let's just consider only this particular yellow elements highlighted in this yellow array. this one particular column. Now, the thing is that if we actually try to find or apply binary search over this particular column to actually find our target, right? So, how binary search will work? We need to define the very starting position and the ending position, and we find the middle index. So, I'm just not writing it down, the left and the right position. I'm just stating that very first uh, binary search over first column will be like the left will be actually 0, the right or the ending index will go is going to be what, rows minus 1. Okay, and our column is always going to remain 0 in, because we are actually searching in 0th column. So our matrix will actually be will become linear now, like it will be kind of a searching or applying binary search in linear matrix, right? So our rows will always change, the rows will change, but the column will always remain 0. Okay, in this situation. So now if we apply binary search over this thing, we can state that 27 for let's just say there are fourth index, this is fourth index, this is zeroth index. So by binary search the middle index is going to be 2. Now we compare, is 20 or 27 target is less than 14? It is not. Is 27 greater than 14? Yes, it is. Since 27 is greater than 14, we can be sure that 27 cannot be lying before this 14, right? So, based on the principle of binary search, what we will do to go right? We will we will increment our left by mid plus 1. So, to explain it more clearly, let me just make this column into a linear matrix. So 1, 5, 14, 14, 31, 33. Okay. And for most of you who actually got the hint, like what actually needs to be done, you can pause the video and go ahead and try to implement it or try to visualize it how I am actually going to proceed further. Okay. So now if we consider this particular column as a linear, array, this is again a linear array for us only. So our last index in our very first iteration, okay, in our first iteration, our left is going to be what? Is left is going to be 0, right is going to be 4, and the mid is going to be 2. So target is what, greater than our mid. In that situation, what we do? We actually increment our left from mid plus 1. That is, left is going to be 3, right is going to be 4, and our mid is now going to be what? It is going to be 4 plus 3 by 2. 4 plus 3 by 2, that is 7 by 2, that is 3, right? So now if we consider third index like 0, 1, 2, 3, this is 31. So is our target, that is 27, is our target actually greater than 31? It is not, right? Here our target becomes less than the middle index, that is 27 becomes less than 31. Here 27 was greater than 14. Since 27 becomes less than 31, in that situation we actually need to decrement our right. So in third iteration what we do is we decrement our right by mid minus 1. So this is left, now right is going to be 2, and this condition is actually the breaking point for us, right? This condition becomes a breaking point for us. So we can clearly state that okay, our target, like the third index 0, 1, 2, 3, that is this. So our target is not actually present in this particular column, but what we actually got here, we break here, right? We break here. So but what we actually got, this third index, what this third index is actually stating us is that there is a possibility. Okay, there is a possibility for this element to be lying in this range. Okay, so like for 0 and 4 it was 2, and for 3 and 4 it became 3, right? So again 3 and it became 3 here. So right. So now what it is stating is that this third index, right? Our target, the last index is was 3, where the condition actually broke, right? So we can clearly state that that last index minus 1, or you can say, you can consider the very last index itself, that our element can either lie in this particular row which is starting from this index, that is 3, or our element could lie actually at an index which is less than this particular, right? Our element could lie at the index which is actually just less than this particular row, that is 2. Okay, or we can, just for hand practice, we can say that since our breaking condition is going to be encountered at a situation where elements to the right are actually greater than the target, or actually will be going to be greater than the target, so we need to actually search for this element at the rowth index minus 1 always. So in the second row, we are going to search for our element. So our target has the possibility of lying in this particular row. And then again, we will apply the binary search over this particular row to actually search for the element. Okay. So this was the basically the approach where we actually apply binary search over the column, and then once we found a particular index where there is a possibility of the element lying, so in that particular row index we actually again apply the binary search over that row to find the target. Okay. So let's just code this one out, this binary solution. So binary search. Okay. So first, we need to define the indexes. Like there is going to be a left index, there is going to be a right index, there is going to be a matrix of numbers, and there is going to be a target which we need to find. Right, and its return type is going to be Boolean because we ultimately return the Boolean. So this we can actually shorten this out, and now we search the binary. So while my left is like less than equal to right, this is the very core or crux algorithm of binary search, right? We find the mid index, that is left plus right by 2. Okay, and if my matrix of what this middle index is like going to that and this, yeah, we need to also provide it a row index or a column index from within which you need to search for. So this is binary search over, let's say, column. So if this is a binary search over column, then we can say that our row is going to change. The mid is going to be implemented over row and the column is going to remain static. So in that situation now, then okay, yeah, sorry. So here, yeah. So here we apply the binary search condition that if the matrix element is less than my target, if my target is actually greater than that, then I increment left by mid plus 1. Else, if my matrix mid 0 is greater, if my target is less than that, then I need to go decrement by light by mid minus 1. Else if neither of the condition is there, then we actually found our element, we return true from here, and we return false in this situation, right? But ultimately we actually require the middle index. If it is a false, we require that index from where we need to search it in a row wise, because this was binary search over column. So we can state that here what we actually need to return is an array which is a boolean or and a number, or it could be a boolean as well. Okay. So here I will return false and the number which is going to be the mid index. So let me just create a mid index that is minus 1. Here it is going to be this way. Let me just consider it as 0. Okay. So here I am going to return mid minus 1. Right. And then this is column wise search. So if the element is actually not found, then we need to actually apply the row wise search as well. So you can actually optimize this code further, and just for clarity I'm doing with search. So in row wise, our row is going to remain static and our column is going to be varying. Okay, and here again, we don't need to have this. We can clearly state that if it is found, it is found. If it is not found, it is not found. Right? So this is the way it is going to be. Okay. So now we have defined our binary search over column and binary search over row. Now what we can do is that we can actually apply this particular thing. So let's just say that let me store the result of column in this particular variable. So binary search over column, it requires a left index that is 0, right index that is rows minus 1, okay, the matrix and the target. The target we can actually specify here, that is 27. If my column of res, or you could say is a column res, if it is an array, or you can say that, let me just state that if type of column res boolean, what that means is that we can return true in that situation, or we can actually state that the element is found. If it is not, if it is an array, then we can state that we actually found a call, we actually found the row index in which we need to apply binary search again. So we can actually console log the result here. So binary search over row, the left, uh, yeah, left is, this is for the column, okay. So this is going to be called minus 1. Right, in which particular row I am actually going to search for. Yeah, so I need to have that row index. Right, so this row index is going to be here because I'm going to search in a row. So that is why that in a particular row, that's why I've implemented the row index here. Okay, so here I will actually column result of 1, I will put it here. The target is going to be 27 and the row, okay, the row index was at the last. Here comes the matrix. So this will give us the final result. Okay, let me just run this. Canonical properties of undefined. Okay, what it is stating is that for left is 0, right, and here our left hand person divided by column is going to remain 0 here. Okay, canonical properties of undefined. Where it is actually giving us this error. Matrix of row index and mix mid, and matrix of row index and mid and 0, right mid minus 1, left is mid plus 1. Okay, left plus right. Okay, the issue is in this particular thing. So since JavaScript is actually returning, it can actually return an integer or a float value as well. So we actually need to consider a floor value of this particular index to actually get a correct integer value to search for. So here I'm going to consider the floor value. Now let me run it and check. So it returned false, right? Since our element 27 doesn't exist, so it returned false. Let us consider 28 now, which actually exists. So 28 and it returned true. And thing is that if we actually also apply, let's say 31, so what do you think? Do I need to actually update that 31 here, or will this code be even running? It won't be. The output would be element found, right? Because 31 already was found in this particular row search itself. So that is why that is in this particular column itself. So that is why row-wise binary search wasn't applied, and we found the element, right? So element found in column, which will make it more clear. So this is how this thing will be working, and let's just consider one more thing, that is 100. We'll see if the edge case conditions are also passing out or not. Okay, so for 100 it actually gave us false, and why is that? Uh, for 0 throw and 0. Okay, that's the issue. So now what happened is that since our element 100 was greater than this thing, so it exhausted and we returned false, but we didn't tend to actually look in the row. Okay, so ultimately, if the false is here, we should be returning. Oh, sorry, this is not the function. Let me just remove this function. It's causing complete confusion. So right here, we in situation of false, we are returning mid -1, right? So if we consider the situation, right? So what is happening is that for this 33, let's say 0 and 4, we came to 2. Then 2 became smaller than 100, so we incremented left from it plus 1, that is 3 and 4. Then 3 and 4 again becomes 3 and 4 is 7, then 3. So 331, then again it became smaller than 100, so we incremented left from 8 plus 1, then left and right both were 4. So mid came out to be 4 again, and again it was less than the target, so left was incremented by mid plus 1 and it broke. And in that situation, we actually decremented our mid -1. So we were actually searching for 100 in this particular array instead of searching over here. Okay, so right. The ambiguity here is that it would be rather good for us to actually look for the element from the last, right? Did you found the issue with this thing? Why it is failing for 100? Is just because that since for 33 or even for 31 when we consider 27, right, I stated that okay, I can just return mid -1 to search for that element. But what about 100? Right, in 100 the mid was 4 and I returned mid -1, that is 31, this row. It was trying to find the element in this particular row and it failed. But in situation of 27, if we search in this particular row, it would have again failed. Reason being because the greater element, the breaking condition here, that the greater element can even lie on the right hand side or even at the bottom. Okay. While we are searching in the very first row, if we are breaking off or if we are stating that the element is not found in this row or at particular index, we are breaking off, we are stating that the element could be lying even on the right hand side or even at the bottom. So there is ambiguity. That is why what would be the correct approach here is that we should be starting from the last column. Because in the last column, okay, let's just say that if we are searching for target at 27, so in the last column, since 30 is going to give us that index, again 2, right? In the last column, it is 0 and this is 100, right? So this is 0 and this is 4. So we will stumble upon an index 2. For index 2, the target 27 is going to be less than 30. So what we would do? We will actually store the mid value in with this second index, and we continue to search here. Okay, so because our element can be is it might be lying less in position less here or above. Okay, or it would be better to break it off from here as well. But yeah, The thing is that this solution needs to be optimized because it is actually breaking at a one particular condition. So let's just say that I will leave that as a homework for you guys to figure it out and let me know in the comments where I did made the mistake and where I can actually correct it or correct myself. Okay. So if we observe the time complexity in this situation is that we are applying binary search over the complete column and then in that particular column, the row starting from that column. So it would be log n, log of number of rows plus the log of number of columns. That's the time complexity in that situation, and that is the most optimized solution to actually deal with this problem. Okay. So hope you learned something from this and let me know in the comments. I'm just same like you guys who is learning by doing this stuff, and I really appreciate like people teaching me or telling me where I go wrong so that I can correct myself in the future. So thank you guys for watching this video. Hope you have a nice day.